This video will present our work, Implicit Form Neural Network for Learning Scalar Hyperbolic Conservation Laws. This is a joint work with Cheng from Wuhan University and Professor Lili from University of South Carolina. In recent years, deep learning techniques have been applied to mathematical and scientific computing problems, and a large number of excellent research works on learning solutions of PDE have emerged. The first attempt of solving PDE using neural networks can be traced back to the late last century. However, due to the limitation of computational resource back that time, it unfortunately did not attract much attention. Currently, there are two major ways to use deep learning for numerical solutions of PDEs. The one is deep reason method and its variants. The idea is to convert the PDEs into the equivalent variational forms and then solve them using neural networks. The other is PIN and its variants. They use neural networks to directly deal with the original PDEs. Our work focuses on scalar hyperbolic conservation law, which is shown here. Although the deep reason method and the PIN has achieved great success, they still exhibit poor performance in handling problems with strong discontinuous solutions, such as hyperbolic conservation laws. For example, when PIN is used to tackle Berger's equation, an additional whiskers term is often used to ensure certain smoothness of the solution. If the whiskers term vanishes, or the viscosity coefficient is very small, PIN becomes very hard to train and fail to capture the shock waves. Our work is inspired by this theorem, where an implicit form for the solution of scalar hyperbolic conservation law can be formulated as this form. The contribution of our work is to propose a fully connected neural network, IFNN, to learn the solution of a scalar hyperbolic conservation law by using the loss function based of the above implicit form instead of the original PDE. This is the architecture of our network, and a skip connection is adopted to improve the training process. To train the network, we use Latin hypercube sampling to generate the dataset, and then split it into three parts, which are shown in different colors in this figure. The loss function consists of three parts, where the first one, also the essential one, is related to the implicit form of the solution. The second one is related to the initial condition, and the last one is determined by different boundary conditions, including Dirichlet, Neumann, and periodic boundary conditions. The key difference between IFNN and PIN is the choice of the first part of the loss function, and the PIN used the original PDE to design it. For implementation detail, our IFNN is implemented using PyTorch, and we use 6 hidden layers and 20 neurons per each hidden layers for all tests. A DAM optimizer is used to train the network, and the number of epochs is set as 25,000. The hyperparameters lambda1 and lambda2 in the loss function are both chosen as 1. We will give some numerical examples to show the performance of our IFNN. This is an example of one-dimensional implicit Berg's equation with shock wave, and we choose the initial condition as a step function, and the Dirichlet boundary condition is used. From the first table, we see that no matter what kind of activation function in the network is selected, the performance of IFNN is always better than PIN, and the tanh function works better significantly. We also consider the effect of network's architecture on the prediction accuracy of IFNN. From the second table, we see that with the increase of the network's width and depth, the prediction accuracy of IFNN gets better. To compromise the network's complexity with the prediction performance, we choose 6 times 20 as our network's architecture. Then, we consider the effect of the size of training set on the prediction accuracy of IFNN. From this figure, we find that with the increasing of the size of the training set, the prediction error decreases until the size reaches about 10,000, and then the continuous increase of the set does not improve the prediction accuracy. A more detailed assessment is shown here, and we see that the prediction solution by IFNN is essentially in agreement with the reference solution in the whole spatial temporal domain, and IFNN can capture the shock wave very well for all times, while PIN does not. This is another example for one-dimension invisible Bergs with shock waves. In this case, we choose the initial condition as a two-step function like this, and the Riemann boundary condition is used. The comparison results in this figure still exhibit the superiority of IFNN over PIN with the solutions with multiple discontinuities. This is an example of one-dimension invisible Berg's equation with a real fraction wave, and we choose the initial condition as a step function like this, and the Dirichlet boundary condition is adopted. The results shown in this figure demonstrated that both of IFN and PIN can capture the continuous solution very well. This is an example of one-dimension invisible Berg's equation with sinusoidal initial data. And IFNN produces satisfactory prediction, while PIN fails to capture the shock completely. This is an example of a two-dimensional invisible Berg's equation with shock wave. Numerical results in this figure shows that IFNN still capture two-dimension shock waves very well. In addition to invisible Berg's equation, we also investigate the scalar conservation laws for modeling the traffic flow problem, LWR model. Here, U represents the density of cars on the road. When U equals 0, there are no cars on the road. And when U equals 1, the road is completely full. We first Consider the LWR to describe the traffic jams. In this case, we choose the initial condition like this, and the Dirichlet boundary condition is used. Here, a traveling shock appears. Numerical results in this figure shows the pin can capture the shock very well, while pin does not. Another example of LWR is the case that traffic light turn green, and in this case we choose the initial condition as a step function like this, and the Dirichlet boundary condition is used. The results in this figure again shows both of IFNN and pin can capture the continuous solution very well. Finally, let's make a summary. In this work, we propose a fully connected neural network with skip connection to solve the scalar conservation law. The essential difference between our IFNN and pin lies the choice of the loss function. IFNN takes the implicit form of the solution to formulate one of the essential terms for the loss function, while pin directly uses the residual of the original PDE. Extensive numerical experiments in 1D and 2D shows that our IFNN is superior to pin in capturing shock waves, while their performance are comparable for the continuous solution. IFNN have both its pros and cons. On the one hand, the training of IFNN is much easier than that of pin, since it needs not to use the automatic differentiation for calculus of differential operators. On the other hand, IFNN requires the target PDEs to have the specific implicit form for their solutions, and thus the scope of its feasibility may not be as wide as pin. Thanks for your attention.